Good morning to everybody. We are very pleased to present this first webinar of a series by Mobus. Today we have Harry Menon. Harry got two master degrees at the Indian Technology University, and he has more than 30 years experience working with operator, consultant, technology, and service company, both in the USA and globally. He's a geoscientist with knowledge and expertise that run the breadth and depth of upstream oil and gas industry. He has worked in more than 25 basins located both in USA and international in diverse geological settings, ranging from deep water, shelf, onshore through fault and thrust belt setting. So his competencies are in geology, geophysics, petrophysics, and related reservoir and petroleum economy. He has coordinated and implemented several multidisciplinary integrated process flows, holistically combining subsurface model with fracture model and reservoir simulation model to improve the economics for development of source rock reservoir. And he strongly believes in directly connecting the subsurface evaluation to field operation by developing and implementing deep learning, machine learning, and artificial intelligence methodology. Actually, he has been working in this topic long before they become so popular in the wording on the EP industry. So again, very pleased and welcome. Thanks to Harry for accepting this presentation. And so, Harry, would you please share your room and go ahead with your webinar.
Yeah,
And
thank you.
by the way, thanks to everybody for joining us.
Can you see my screen?
Yes.
Okay, let me put it in the thing.
By the way, if you have any question, you can use the chat, send it to me so I have it. So as soon as Harry finish, then I can start reading your questions. And also, well, you can also speak loud when you're in the Q&A session. Go ahead, Harry, please.
Hey, thank you, Jose Luis. Good morning, good afternoon, and good evening all. Thank you for joining Moo's webinar today from different parts of the world, I guess. So I hope you're all doing well. And thanks again for joining in. So I start my presentation on or a webinar on machine learning applications and in geological space. So I would expect this is a very familiar area these days. So it's on there in LinkedIn or everywhere on the webinars and stuff. So what I'm trying to do is that I don't claim myself to be an expert on it. I will be presenting a couple of examples of the work that I've done, which could be implemented and fine-tuned as well with the present day better and improved software that is available in the industry as well as within the our own organization, Movus Energy. So what does Movus Energy do? So we actually present the data science-based solutions, and we actually cover all of the upstream efforts in developing and producing oil and gas. So like, as well as on the training aspects as well. And these specialized digitized tools, licensing and tailor-made digital tools, these are the software part of it, which we partner with the state-of-the-art the software industry, projects and consulting. And we do consulting varying from the exploration to the end of the secondary recoveries as well, or as you all know, EOR and IORs. including the drilling and the production engineering, which comes into that. Change management, design and co-implement, as well as digital transformation and automation, which is again, we design and co-implement along with our partners. What is our consulting services? Like I mentioned, that it covers the entire aspect of the upstream end, including the engineering part, like the construction engineering, P&A, technology, product management, operations, field-based roles, all aspects of the production operations, solving for maximum economic benefits, mature assets, development and redevelopment, and also applying mathematical optimization techniques. And in the classical sense, as the subsurface evaluation, we cover the entire gamut of the generation, maturation of prospects, acreage evaluations, and reserves estimations, both deterministic as well as the stochastic ones or the probabilistic. Sorry?
It's all right. It's all right.
Yeah,
Keep going.
okay.
Keep going.
So, and these are all one of the things that we specialize in under the subsurface realm, as well as the others, is the integration or holistically bringing in the diverse data together, and with the machine learning that is becoming more and more a reality, which has been elusive for our industry. We've been talking on it, but it's always we were not there yet, which you'll see. So before I begin on my slides, I would like to do an acknowledgement or a disclaimer, whichever way you would take it, that I will read this out so that I don't miss any part of it. All thoughts and ideas expressed in this webinar are that of my own, gathered through my work experience, which is direct work, discussions with a number of my colleagues, articles from professional journals, blogs on the internet pages, interdisciplinary applications of data science, webinars, and training on geoscience applications of machine learning and deep learning that I attended. I thank all authors who shared their work through articles in professional journals that I have read, but missed in the reference since I can't put everything. And I do have a reference at the end of it, which says the key ideas and the information taken from them, in the sense of the information is mostly in sense of the ideas, some of the ideas which added to that of my own. Having covered that, let's go. So in today's presentation, what I'd like to address is the three key aspects of the trio, what you call ML, DL, AI, or the machine learning, deep learning, and AI methods. How do we relate this technology to finding oil, developing, and producing oil and gas? Areas in the subsurface realm, the technologies, how is this technology making its presence felt? Right, so where these technologies are making its presence felt within the subsurface realm. So the focus is only on the subsurface realm here at the moment. What approaches are used in the subsurface space? So I hope these objectives will cover at the end of the presentation, and anything that's gone missed out and your questions, they're always welcome. Let's go through the agenda. So what do you expect? This is a snapshot or a preview of what comes through the presentation. I'll start with distinguishing machine learning, deep learning, and AI. This is, most of you, maybe all of you, not most, I'm absolutely certain that all of you are aware of this. But just to give a context to what I'm talking, I would give a brief introduction to these three techniques, as well as relate this technology to finding, developing, and producing oil and gas, like I mentioned. And what are the areas in the subsurface realm the technology is making its presence felt? And all the roadblocks in technology implementation, are we there yet? How to make the technology a general process flow for subsurface evaluations. I'll just like to mention here a bit that there is much more heavier or a lot introduction of these technologies into the operations side. But in the subsurface evaluation side, it's still lagging a bit. And though there are bits and pieces and people are working towards it, and there's lots of good ambition as to where we will be going, working towards it. And then I will give you a couple of examples, the approaches used for specific solutions in geological space, which will give you a teaser. And since I can't include every aspects of it, I have given sufficient information over there so that you can appreciate the use of these ML deep learning and AI methods. And then I'll conclude with the summary of and the other areas of applications, takeaway, references, and then Lewis would come in to say what is the next aspects in the MOVUS is moving towards in terms of the webinars, training, etc. Okay. So you start on the distinguished machine learning, deep learning, and methods. So there are three types of machine learning. It's a building block for developing for deep learning and artificial intelligence. They're using statistical methods to enable computers to learn with experience. Well, basically, what we're doing is that extracting patterns from data, which is a very common approach we have been doing for a long, long time. It's the only thing we have been doing with our manually, and what we're trying to exploit is the power of the computation as well as the softwares that are come up, or the algorithms that are developed to discern this integration or to get the information. What are the types of machine learning? It is the supervised learning, which has each input has a corresponding output in the data set. That is, there is a training data set, and you develop a relationship using the relationship to forecast, like the regression and the classification methods. And there is basically they are the supervised ones, or the task-driven, or which is basically on predicting the next value. So let me get a laser pointer. Okay, I can do. So you could see here on the right, bottom right, a types of machine learning in terms of the classification that's been there. What are the types that are available today? Unsupervised learning, it's a clustering or grouping of input data set based on patterns, and that is more closer to the pattern recognition and basically bringing in the concepts as well, using the concepts and machine learning those concepts and applying to identify the clusters of data. One of the things is this identifying seismic reflection patterns, distinction between different clusters of these patterns. And this is one of the examples that I'll be going to show you. And the other one is the anomaly detection as well, which is coming and becoming more and more. It's being applied today by various, by different companies or the software companies, but it's not yet been a regular one by the practitioners or the operators. There are some of the consultants who do use them. Reinforced learning, this is one of the complicated ones, and which is actually a machine learns over time on models, learn from mistakes, basically, get awarded for performing desirable actions. And for me, at least, it was a surprise that been doing this since possibly 2 decades, that Monte Carlo simulation for oil and gas reserve estimation, that falls under this reinforced learning. And it is pretty involved one, and it's quite an interesting one. I'm still not, I don't have the grip on it. I know the processes here, but how does it relate to the reinforced? That is something, it's a bit more complex than the understanding the supervised and unsupervised learning. Deep learning does the next step level up. It's a human brain inspired systems. Basically, it's a predictive models through artificial neural networks, network algorithms. What it covers would be the large volumes of data, uncover hidden relationship between large number of variables. This hidden relationship is the crux of it. And it makes humanly almost impossible to do it with the large volume of data. And it's a sophisticated pattern recognition. the way it is to be understood is that its construct is through layers. So there is an input layer, which is receiver or which is receives, and there is a process. This is the hidden layer, which determines through the various permutations and combinations, the relationships, the hidden relationships as well, and then outputs, which is a transmitter. So that is the best way to understand how the DL method is. And the way that how the DL method differs from the ML method is that ML method has only one hidden layer. I want to bring here one aspect that the distinction between these deep learning and the machine learning is very thin. So it's not that this is deep learning and this is the machine learning. So it kind of amalgamates or mixes. One of the examples that we use in the subsurface evaluation, most often used and which can be very well used, is the Lithofacies classification methods. And it has got an implication in almost all of the subsurface evaluations because it gets directly related to the production as well. Artificial intelligence, it's a smart intelligence systems enabled to make human-like decisions. Okay, so these we are not yet there, but there are been attempts, actually initiatives taken by the companies for applying the artificial intelligence. Mind you, here I'll be referring to the, as I mentioned, on the subsurface realm, whereas there has been in the operational areas, just to quote an example, is detecting oil seeps with AI-powered robots. Like, for example, Exxon is working on, along with MIT to develop that. And also, many of you all may be aware of the using drones to map the outcrops. And once they map unreachable outcrops, and then use those images to construct a 3D model. And constructing 3D model, you can slice them, and like any of the 3D seismic of the outcrop, and learn from. So that is developing a lot for the educational purposes as well. So these are the systems relating to thought processes. It's reasoning and behavior. The focus is more on the success. Basically here, what you're looking all the time, we were looking at the accuracies, but when the AI comes in, it is directly the success. So there is a shift in the perception as to how we apply the artificial intelligence and what to expect from it, because it's creating unique knowledge base and perform predictive analysis just like the human beings, and using all these machine learning and deep learning algorithms, so. But there is one thing that is there, which all of you must have come across and must have practiced more regularly in your routine process flows or the workflows: data analytics, which links traditional statistics with computing technology and domain experts' knowledge. That's very important. So the familiar example or popular one is the resource play analysis or the shale play analysis, which is set up as a statistical play. It is perceived and applied as a data-driven model today, and it's actually a shift from trendology or trend-based predictions, which has been for more than 8 decades or 7 decades, has been most often used in the exploration as well as in the development of the fields in terms of the analogs or looking at the trends and predicting the next big find. And it's been very successful. But with the data coming in and with the data-driven models, it's going to be more exciting. So a summary out here, how they are ranked or the hierarchically is that starting with the data analyticals, basically it's relating data analytics, all these MLDL and AI within the subsurface geological space. So data analytics, it relates variables. And then you go on to identify and extract patterns or the classifications using the machine learning. And with the deep learning, as I mentioned, it has got multiple hidden layers. So it's improved accuracy in prediction. And when the artificial intelligence, it's creating the knowledge base and combines DL and ML technologies. And here, I just thought I would put this one across to show that was the initiative by Total SA and Google Cloud is they are trying to interpret seismic images using computer vision technology. This got started in 2019 or early 20s, automating the analysis of technical document using natural language processing. This is pretty interesting. So if that comes in, what you'd have is that you would automate most of our work process or the workflows for the identifying for the exploration as well as the appraisal and development, the cycle of the subsurface evaluation. And areas in the subsurface realm where the technology, how does this technology improve finding, developing, and production of oil and gas? Well, the business of E&P industry is to provide a successful forecast. This is the most fundamental thing. And of course, that forecast is within acceptable margins. We cannot eliminate that. It's always a prediction is there. It's not never 100%, and that is not the way to look at it either. So from the what we're saying is that this is, again, I have not considered the other important aspects of engineering, drilling, completions, and production, which of course is a dominant part in the forecast as well, for the successful forecast. And here the figure that you'd see here is taken from the, so it's a near field exploration example. It's a work from the authors by Rocky Rodden and Deborah Zachary from the Paradise or Insights. And they're doing a lot of work and in the self-organization map method, which uses both the uses the complex self-organization method application along with the principal components. And that's been proven to be successful in identifying, at least in this case, is the near field application for the near field exploration. So there is a field over here with an anomaly, and there's an undrilled anomaly away from that, and that's a deeper level, and that would become a near field exploration target. So this kind of predictive thing is very, is highly useful and in reducing the speed and bringing in the solutions that actually reduces or increases the POS or the probability of success. Now, the problem of prediction, what it is, it breaks down to the convergence of choices learned from analyzing past behavior and determining the relationship between a large number of variables to forecast a future or near future behavior. What you need to have is a successful outcome, and that, of course, depends upon the economics of the times. Can this be based, the question that I have is that, can this be based only on statistical methods, that is the data analytics, like I mentioned earlier, or is there a hidden relationship between the behavior and the system, that is between what you see as the behavior pattern, the end pattern, and the system, which is the physics? So what these technologies enable working with large volumes of data. No data left behind or ignored is the object. It's a big data. All of us have heard about the big data. So big data is nothing but a combination of high volume. High velocity would refers to the speed at which the data is, we are receiving the data. And also the heterogeneity, the different kinds of data. The image data with this, the subsurface seismic, well data, you get the sampling, the core data, as well as the cutting. So all this data, and also the historical data. So none to be left. So when you combine all this data is so huge. So that is where these technologies enable us to work on that huge volume of data. For speed and success in prediction or forecast, and also to combine data-driven and physics-driven models, which I mentioned earlier, and there could be a system behavior. Can we derive the system behavior which drives the statistical relationship between different elemental properties to forecast a commodity or success? And this, when I mention here commodity, because if you jump across the other sectors, like most popular being the movie sector, entertainment sector, which is the Amazon and all using, and Netflix, the way they predict your, or even the Google as such, or the internet, which predicts your behavior. So that is the best example that you have on the AI, very successfully implemented, and possibly we can do this with the data as well, using the data to predict. Exploitation of resource play introduced big data analytics into oil industry. Moving beyond data analytics is to incorporate these methods, MLDL, AI methods, in the E&P process flow. That's the objective that we got to look at, and it's coming. Of course, we all know about it. So, what are the perceived roadblocks? How to make this technology a general process flow for subsurface evaluations? There are certain things of black box implications because the algorithms here differs from that of the conventional algorithm. You do develop a conventional algorithm, you code them, and you test back them, you know the process and things. Whereas here is, if you take a neural network, the way the combination is going within the hidden layers is still a black box. So these logics are not explicitly written like that of the conventional algorithm. So the issue that comes out of it is how to estimate error and analyze it. Is there sufficient rigor for validating system? We are validating with the blind well test and the others, but is it sufficient? Is there a sufficient rigor? Can we develop a sufficient rigor? These are the areas where it's been working and it's been improved a lot. And I think we'll be there very soon. Can we characterize specific model behavior? Can developing efficient and complex systems that is combining deep learning and AI will increase the accuracy or the confidence in the results and overcome the black box implications? And the answer is yes. It's a, we have come here, like also Luis mentioned, that we have been applying it for since long, before these are coming into the into our industry. The only reason it takes a turn is because of the improved algorithms and the improved ways of applying the very same processes and concepts by reducing the, which has an implication in reducing the time as well as the increasing the accuracy. And using, most importantly, using all the diverse data that is available within our industry, which we have been having it, which we are quite familiar with. Particularly the volume of data. So we'll go into the examples. Like I mentioned, I'll go through the two of the examples. In the example one, it's application of unsupervised machine learning used for prospect generation and assessing geological risk for drilling. So what's the problem was that it's a prospect generate prospects and identify critical geological risk for drilling within an offshore exploration lease. The challenge was to identify the reservoir facies and its areal distribution. There are others too that have been used to, like seal and the other geological factors, but I'm focusing here only on the reservoir risk. And in those two, the seal and the other risk that has been, particularly the seal risk, was also used, was identified using the similar method, the same unsupervised machine learning method for the seals instead of the reservoir. The data you had was the 3D seismic and 2 offset dry wells located 20 kilometers away from the 2D survey, and they are calibrated or connected with 2D seismic lines. What was the process flow? Is they identify, this was the 4 to 5 steps of the process was the workflow included identifying seismic sequences and isolating the target sequence containing the reservoir. Like, let me go in, sorry. Okay, so the shaded one is the sequence that we are looking, and within that sequence is basically the reservoirs and the different elements of the reservoir situated on it. So this sequence has been subsetted into a seismic subvolume defined by the top and bottom of the sequence, which is here on the blue and the red, and then use that for that particular sequence or the subsequence subvolume, if you will, run unsupervised k-means classifier, which is the groups of similar, which will, they are expected to group similar waveforms or the reflection patterns, as you see that there are different reflection patterns on there, which are in turn are reflecting the changes in the rock type across the lease area, which we run through the subvolumes and then across the lease area as the subvolume. So the output will be the grouping of or the clustering of the similar reflection patterns or classes, as we called across the lease area. Interpret reflection patterns for depositional patterns here is where the seismic facies to geological facies, which is the seismic stratigraphic concept. So the concept is proven. So if you can identify these patterns and if you work that way, that is where still you have the human intervention. So these are the processes. If you could automate that kind of human intervention process, then you would have the AI coming in. So that's the sequence. So with the K-means classifier, we identified 4 classes or groups that, let me see that, okay, that correlate with specific reflection patterns of the seismic facies. And what you're seeing is the summation of all the 4 groups, class 1 being the white, or the overlay of all the 4 groups, if you will, not the summation, sorry. So you have the class 1 as the white, and the class 2 the green, class 3 blue, and class 4 deep or dark magenta, which you'll see that hidden along that. Now the idea is that these 4 classes, how do they reflect in terms of the seismic reflection, or what did they group them? So the class 1, which is white that you would see in the left picture, is actually parallel to subparallel reflections, which you have seen in the earlier picture or the image of the seismic line, which I showed you, which is within the lease area. And this parallel and subparallel has a connotation in terms of the depositional facies or the geological facies. Or depositional environment, if you will. The seismic facies class 2 has got the parallel and subparallel, but they are shingled. And you could see there's some part of the shingling out here as well, like, you know. So this is the second type of the class, seismic facies class. And the third one is the mounted to chaotic and reflection free. And the fourth one is the wedge or the divergent type. Now, all these, just to give you a background, is that this is a carbonate. I purposefully did not mention earlier. It's a carbonate shelf environment with a shelf slope system, so you could have an idea as to what we are getting at. Okay, so with those reflection patterns or the classes, what you would say is that you can interpret the geological facies or the depositional environments. So you have here the carbonate shelf ramp and slope for the class 1, and then when you see the class 3 and class 4, you see that they can be interpreted as the reef and constructed through the stacking flat to pinnacle shelf words. That is the depositional interpretation, and you see that that is within the shelf to shelf margin and near distal part of the slope. And you have the debris flow as well as the fan. So if you isolate this classes 3 and 4, we should be able to see the reservoir distribution. And also each K-means class, that is class 1, class 2, class 3, also represents a particular geological element, or in terms of the risk of a particular geological element. In this, whereas class 3 and class 4, the distribution of reservoir is the geological risk can be perceived in that way as well. And the other one, just to mention here, is if you look at the aggradation increase of parallel to subparallel kind of a thing, they would represent more or less the possibility of the shale. And this has been subjected, or the seal rock. So where there is an accommodation, there's an increase in accommodation, a gradual deposition, either it's a deepening, so you will not have much of the porosity developed within carbonates, or you will have a clastic input coming in. So that is another process that within this particular method we'll be using to identify that risk element as well. So isolating the seismic facies class 3 and 4. So what you'll have is, what you're seeing is the reservoir distribution. And you'll see this is on the left is the mounted to chaotic reflection free, which is the reef possibility of a reef out there growth, and then away from the divergent one, which is shows the apron or the debris flows. And this all the reds is actually one aspect of this class 3 and 4 combined is what you're seeing here, isolated anomaly for the reservoir. So using the other attribute methods of the seismic, you're able to derive what you see here is the shelf slope, carbonate architectural elements. But if you see that, what you have is a morphology, but you don't know what is what, where is the reservoir, where is the seal, or what is non-reservoir kind of thing. And when you isolate them using the machine learning, so you could see that the reservoir distribution on there. And by outlining the morphology and overlaying it, you will see that this is how the morphology is overlaid, and you could clearly see that how the reservoir is distributed within that particular morphology. And all the blank areas are where there is no reservoir. Now, one of the aspects is this being a picture, what you'd see is that one of the questions that would come up is that how do I identify now the reservoir exactly in terms of quantification? So since this is a 3-dimension, you could do that in terms of taking slice after slice and looking at each depth slices, if you will, or you're identifying a location, and at that particular location within a diameter, you could look up and see whether you're locating your exploration well in the right place so that you will mitigate or minimize the reservoir risk. So with this example, what we've seen is that what did the unsupervised machine learning give us is the reservoir facies classes are predicted by classifying reflection patterns for the entire 3D. So what would happen is the speed and efficiency. If you're going by the traditional, I mean, with the even with the 3D interpretation, it would take a real long time to complete this process. Whereas if you can run this unsupervised, it's basically done within it's in minutes, but including some of the interpretations that are there is within hours, right? So that is a huge compaction of the time. And the reservoir presence predicted for the architectural elements of the reef systems. We know that it's a reef system, so we should be able to predict them, and we get a better prediction of it. We could see that. And the reservoir risk is mitigated for the prospect, like I mentioned before. So the unsupervised machine learning is very much applicable and effective in prospect generation. So one of the key outcomes of this is the compression of the time and using as much data that is available for the task. Example 2 is I picked up a application of a supervised machine learning method, which is the probabilistic neural network. It's one of the earlier methods, and there are several further advancement in the neural networks as well. And it's been used for the lithofacies classification. Again, as to give a background on it, there's been a hydrocarbon discovery within the turbidite channels, and they've been appraised as well. They've been appraisal wells, and it was needed to identify the drilling locations for the field development. Well, the challenge was to define the architectural elements of the reservoir channel system. So here again, I focused on the reservoir facies because that becomes an important, see a reservoir quality or the reservoir facies that is related to the petrophysical properties, and see that where these reservoirs, effective reservoirs are present. And if so, can we quantify them? And this is a channel system, so deep water channel system. So it is proven to be hydrocarbon saturated by the discoveries and the appraisal. The requirement was to map areas of effective reservoir. That is the reservoir, in other words, the reservoir presence. Well, the data had the 3 discovery wells within the channel systems and 3 offset wells and 3D seismic volume. The process flow, define the lithofacies from the well log, all the data that is there from the well logs, well data, which is cuttings, logs, and core descriptions, and build a lithofacies model at the wells. Or there are 3 wells, remember. And you discretize lithofacies classes to litho curves. Extract all possible seismic attributes from within the sequence of 3D seismic volume. You don't have to care whether this volume is, this particular attribute is relevant or not. So if there are about 50 or so, as many attributes that are there, just extract them and let the machine do the correlation, see what is significant and what is not. And one of the attributes that you would, which is not in a classical sense considered as an attribute, I strongly, I mean, the way that I look at it, even a seismic inversion is an attribute. That's how I looked at it and included that as well. And train these litho curves from the lithofacies model with multi-seismic attributes using the probabilistic neural network, validate them with the blind well tests, and apply the trained network results to the 3D volume, which creates the lithofacies distribution, as well as the uncertainty volumes, which are the probabilistic volumes computed from these outputs. And extract the reservoir facies with uncertainty in both in 2D, that is the map-based as a slice, as well as in the 3D based. So this is what you'll see as the example, giving you the snapshot of the complete process flow. You could, what I'm seeing on the right, you're seeing is the turbidite channel system. What you're looking at is a spectral decomposition identifying the channel boundaries very well in this case. And the gray strips that you see here, oops, sorry, are the well locations. And this particular log that you're seeing is at that particular area. And that what you're seeing is that within this particular sequence or subsequence, if you will, you got the responses of the 2nd order and the 3rd order depositional sequences. This being the 3rd order, the red and black, and then the other smaller ones as being the 2nd order ones. And the lithology that is interpreted using the gamma ray log, magnetic resonance log, as well as the core descriptions and well cuttings, and also the derived capillary pressure also have been used in this case to determine the lithology. And there are 4 main litho classes that are identified. Litho class 4 being the coarse sand, which is yellow, medium sand, red, siltstone is ochre, which is, I don't know if you could see that, that's very, very subtle out there. And then the here is the ochre. And then you see the light brown, which is the mudstone. And here's an example. It's a different location, not for the same one, but here, I guess, is the lithological strip converted to discrete litho curve. So what you're seeing is that this is the litho curve and this is the lithology strip. Okay, now when you train this litho curves multi-seismic attributes, this is a typical training data set. And of course, these are validated through the blind test as well. So on the left, you'll see is the identified slope channel and top base. This is the litho log, discretized litho log. Or a litho curve, if you will, and then you got the amplitude, and I put in about some attributes over here. And similarly, at a different location, these are the similar attributes within a particular interval as such. And what you would see is that by the neural network, what it did was that it has taken in all the seismic attributes that that we are given as the input, computed everything, and it determined the relationship and trying to find or uncover the hidden relationship, sorry, no problem, yeah. Hidden relationship that could be there. And you'd see that not all, as we know, not all attributes are significant. So they basically, what you would take is that the first 3 or first 4, first 5, which are significant in the response or having a relationships are used to mimic the lithology or the lithofacies in the area. So in this case, the total number of attributes computed are about 33, sorry, and total number of correlation sets is 285. You would appreciate that all this, to do that manually is real. It's almost impossible. So this is where the machine helps us to determine these relationships, and the better and better algorithms we develop, the better, the more confidence, or the more reliable these correlation sets would be, or the results would be. So here are the results of the trained neural network applied to the 3D seismic volume. And basically it's a lithofacies distribution and uncertainty volumes. What you see on the left is those 4 classes which we are talked on the logs, litho model from the wells, have been distributed with the seismic using the training data set, wherein here the yellow represents the coarse and coarse sand, which is the litho class 4. Red represents the medium sand. You see that red very slight on that. You have to look at it carefully, because what you're seeing is that is a 3D, it's a 2D view of a 3D volume, right? From the top, it's from the side, the top side, if you will. And the blue is the siltstone, which is the class 4, and the cyan, which is this one, is the mudstone. Basically, what you have seen in the earlier figure, or the image, which identified the boundary by the spectral decomposition, is the boundary of the channel system. Now what you're seeing is within the channel system, and within the channel system now you will be able to see which is the levee aggradation and which are the splays. And here is just the class 4 and 3, which is the sandstone isolated from this. And you would see that how it is with this is not the end of the channels though, the channel system. This is the end of the channel system where the cyan is. So this is actually a subset of that you would know that which are the areas to go for the development, right? And then what you see here is the sandstone. This is a sandstone, as we are seeing, is now we need a quantification. Okay, if I drill there, what is the probability that I would hit for that prediction, the sand? So what you do is that what I did is that to use the sand and compute the probability for the sandstone presence. So what you would see, the color depicted here, again, blue to yellow, is that when you go onto the yellow, is the probability 1, and the blue is the probability 0 point something, and that very, very low. So what you would see is that, again, where the probability, when you, suppose if I put a location out here, the probability of hitting a sand there is very high. Whereas anywhere here there is sand, but we don't know in a quantified way, okay, what is the probability of my sand? So that's why the prediction is always, it's a prediction which has got within the marginal limits, and quantifying that is a great advance, and it's very useful for the, for the POS, or the probability of success, or even locating the development wells and have the increase in production as well as the reserves. And this is, as I mentioned earlier, is computationally intense, and of course it's fast. There's higher confidence in identifying architectural elements of the channel system, or else we'll have to identify only looking at the image. And also it's a better control on reserve estimation and better placement of the drilling locations. And all these points have been used for developing this field. So the supervised machine learning can be effectively applied for the field development. So we have seen these 2 examples, right? So unsupervised and the supervised applied through the cycle from exploration to the field development. So in summary, what you see, they demonstrate very clearly the capacity of machine learning in solving the basic problem of the input industry, of the E&P industry, which is to successfully forecast within acceptable margins. That's our business. We are forecasting all the time. That's the business of the E&P. And we are using all these data as tools And the good thing with the development of the machine learning, all this trio, as I call this technology, is our capability of implementing that and implementing these technologies for the large volume of data for a long time, which we have been ignoring, or because we have been selective. Let me put it that way. We've been selective in choosing what is relevant. So by including the machine learning techniques in the ENP process flow, it's high time we have to include that as a general routine. We'll be able to generate and mature prospects, to build subsurface reservoir models, to identify optimal well locations for field development, and to quantify geological risk prior to drill. I've covered all this in the examples that I've shown, all these points, and whereas to build the reservoir models is where your reservoir distribution would go into that 3D geological model and develop that one. And it's an input to the 3D geological model. And of course, the advancement will be to construct the whole model with the machine or the deep learning process, if you will. What is the advantage of the technology? Ability to work large volumes of data, increase speed and success, like I mentioned before. And the key one, which is my favorite, is that ability to combine data-driven and physics-driven models. We are not there fully yet, but halfway, yes. And there is a strong inclination that we are reaching that aspect of it. That is from the statistical relationship predicting the system behavior. It is an enabler. This technology is an enabler for analyzing large number of variables, right? So it's earlier I mentioned about the data, but we got to look at the data, looking at it deeper is the large number of variables, okay? And I mentioned at the beginning of the webinar that it provides the integration of diverse data for predicting successes. This integration has been elusive. And the combination of these trio will help us in combining the data-driven or the statistical and the physics-driven models to improve our prediction. Yeah. Next one. So what are the other areas of applications? So in MOVIS as such, you know, so we are involved in doing several working on the projects that are related to the applying the machine learning and the deep learning methods to water flood and stream flood project optimization. This is also an upcoming MOVIS webinar, which I strongly encourage you all to attend. Here, what you're seeing is that the data science, basically the flow that is there, and this is the Darcy's equation. The physics of it is being related to the data science and machine learning, and the output is a fuzzy logic. You know, as you know, that fuzzy logic is an AI. It's an AI band technique. Basically, it is a AI technique for predicting and reasoning, for predicting with data with incomplete data, or if there is a data gap. So that is one of the best logics to apply to determine the outcome or the output. So MOVIS works along with the techies to put the solution, and you could hear that from Jose Luis. It will be, I think, possibly next month in the MOVIS webinar. And also improving forecast with decline curve analysis for mature fields. That's also an upcoming MOVIS webinar, which will follow the water flood webinar. The resource place, this is the other area of application. We could move beyond the data analytics. Data analytics is a routine process now. So whereas we got to move beyond that by bringing in the machine learning aspects of it for a better correlation, moving beyond the two-dimensional or the simple regression analysis to more sophisticated machine and deep learning processes to optimize the hydraulic fracture design, completions, and well spacing again. Of course, the application of AI, which is the goal of this trial, is in geoscience and engineering spaces under active development. So basically, as I mentioned before, is integrating the subsurface data to create unique knowledge base. That is the human thing, and to perform predictive analysis by combining machine and deep learning algorithms, mimicking the human behavioral system. And we are reaching there. So what is the takeaway? And what is it that this, apart from the applications, by now I'm sure that you all are convinced, or maybe you're already convinced, but you have seen the application with a different perspective, not with reference to a software perspective, more in reference to the application perspective, and the softwares are there, are being developed. Let me put it that way, like the MOVAs along with the TACs, we are developing some, we already have some that we can work and ready to work on. So the team, we as a team have the skills and expertise. We got more than, possibly 500 years of experience or so with the team and applying, with the domain expertise. And we are into, as well as the software, the younger software developers as well within our partners, and applying these machine learning methods for optimal asset acquisitions. If there is any asset acquisitions, we could do it, and I'll let you know how that is in brief. Generation and maturation of prospects, prediction of reservoir properties, like also which goes into the building into 3D geological and reservoir models. And we would use the machine language aspects of it in the geological and reservoir models as well. And identify optimal well locations for field development. You have seen that in the example, and also the quantify geological risks prior to drilling and doing this prior to drill. And that is a huge need for the success, or for the probability of success. The impact and benefits of these are that you can review publicly available data. That is for the optimal asset acquisitions. We've got court records, land data, and production information. There's plenty of these public data available. And within the US, if you're looking at the US mature prospects, or even the shale, the unconventional ones, how you would do this very quickly. This is where we are moving away from the, we are stepping ahead from the data analytics to the applying the machine learning methods here to compress the time and also use the huge data that is there. And the integration, which is the most favorite of me, integrating all data, that is no data left behind. That is how I see it. Enable informed decision making, that is quantify uncertainty and risk. If you have that for the managers, it becomes easier to understand understand the risks and the uncertainty in the whole process, as well as can make decisions that are informed rather than based on some assumptions which are or half information, if you will. Increase reserves and production with field development. So you have increase in reserves as well as production. And here not mentioned that there is also decrease in the lifting costs, which is kind of related to it. I didn't bring in that economic part of it, which is again a big, you could use those economics, machine learning part for the economics as well as a method of the decision tree to see, quantify your bring the decision tree to make those informed decisions, if you will. Improved probability of success for near field exploration. You've seen one of the examples there from the Paradise, from that publication in GeoExpro, where how it was used successfully for, and that's a success, of course, for the field exploration. These are the key references. They have been one of the figures, a couple of figures that I have taken, particularly the seismic interpretation with machine learning, that one, which you see in GeoExpro. So you could go and look there for that methodology with the big data. And the rest of the ones are the various aspects which have made me build the application, as well as to use these methods that were available in different softwares and combine them to present the results that what I have presented. So with that, thank you for your patience, for attending, and I'd be appreciate if you have got any questions, please, like Jose Luis mentioned, send it to him, or so I could be able to answer the questions that you have already logged in. So with this, again, thanking you all for your patience and for attending the webinar. Appreciate you all coming in from your busy, putting the times on for attending this. And with this, I will hand it over to Jose Luis, for who will go through the next activities and also the question and answers. Jose Luis.
Thank you very much, Harry. Yes, let's open the question and answer session. You can either send a text by the chat or voice your questions. So, section open.
Harry, this is Alexei. Very nice presentation. I wonder if in the case of the same, more or less the same fields with few wells and small information regarding seismic, think about that. This is a naturally fractured reservoir. We have only 3 wells. We have a 2D and 3D seismic and some attributes interpreted. What model do you recommend? The unsupervised or the supervised method to build it for a naturally fractured network?
Yeah, now it's an interesting one. So because when you see the naturally fractured reservoirs, it has a pattern all the time. It has a pattern, and one of the powerful applications in here is the effectively using the fractal geometry. So if you identify these patterns in these 3 wells, and if you have a model of that pattern, then we can use a supervised to see similar models with the seismic 3D. And also simultaneously, you can do an unsupervised one and compare these two, because we got very less wells for validation part. We are using the wells that are 3, so possibly you'll use 1 or 2 to you will use all the 3, leaving each of them as a blind test developing in the supervised case. So, but at the same time, if you do the unsupervised, then combine these 2, that will give a better confidence on it. But it is very much doable, and this is where this actually shows its power. The main power and the validation is here is drill a location and see that it's successful.
Okay.